Okay, so let's actually get on with programming. Tomathius's build of PCAS or Magic Kit that we downloaded, that's what we're going to use, and that's all we'll start with for now. I've made an assembly file called tutorial.asm, and here it is. Right now it's blank. Go.bat I've edited to assemble tutorial.asm, and that should work, maybe. But anyway, so let's load it up, and every assembler has different directives that are needed to define banking or what's listed, not listed, etc. So let's first just set up what's needed, and so this just tells the assembler to list all the assembly opcodes and macros as well as we assemble our file, so that it doesn't leave anything out in the assembly listing, the LST file which it'll generate. So what we basically need to start up is to set the bank. And on the PC Engine, the default starting bank is 0. And they're 8K large each, so they all span from E000 to FFFF. There we go. And for now, this is code. It's not data or anything like that, obviously. So, well, we need to reset the CPU. This is the reset routine, and the reset vector on the 6280, of course, is right at the end of FFFE, so we'll need to define that vector, right away as we start. So, way at the bottom, Alright, so no mistaking that. If the CPU gets reset, or if when the emulator starts up, it'll start at our code reset right here. Okay. So when NME 6502 first starts up, it should disable interrupts. That's what we'll do. SCI disables all interrupts from triggering on the CPU, even though they might be generated elsewhere in the system. So SCI is set interrupt disable. And of course the 6280 starts in low speed mode, so why not kick it into high speed mode right away? Set high speed. CLD, pretty standard, clear the decimal mode flag. Okay. And on startup, of course, the CPU has all banks filled with ROM, basically, bank 0. So we need to map in the I/O and map in the RAM. So bank FF is the I/O, and then again we use the TAM, transfer accumulator, to MPR, memory mapping register, and that's 0. In our assembler, we do TAM 0, 1, 2, 3, 4, 5, 6, 7, but the actual opcode will translate that to TAM 1, 2, 4, 8, 16, etc. So it's a little bit confusing there, but for now, memory paging register 0, we write TAM 0. Memory paging register 1, we do TAM 1. Okay, so with this, the I/O is mapped in. Okay. Transfer that accumulator. Right now it's FF. Transfer that to the X register. We'll need that later. F8 is the bank for RAM, so we need to map that in as well. And that's transfer TAM instruction. Transfers the MPR 1. Okay. Well, that's basically it for mapping things in. Maybe I'll make a space. Sorry, transfer x to the stack pointer. So we transferred a to x, and so x contained ff, and then transfer that over to the stack pointer. So now the stack pointer points to ff, which means the stack is now set at 21 ff in RAM. Okay. And just to have fun, or just to be safe, I'll load A with what's at 0000, and that's the VDC status register. And reading that will hopefully clear interrupts. And then to actually clear the interrupt mask, sorry, 7, mistyping. Okay, so the first 3 bits of 1402 are the IRQ mask for the vsync, vblank hit, as well as hsync and an IRQ, the timer IRQ. So we want to ignore those for now and turn off the interrupts for that. So 1402 is the acknowledge for is the masking register for enabling or disabling these interrupts. And actually, a bit set means the interrupt is disabled. A bit cleared means that the interrupt is enabled. So I'll note that. All right. I guess I should add a few more comments if you want to look at this later. So very general comments I'll just do, or map in or bank in IO, map in RAM. Okay, it's a tiny bit messy, but this is just the basic things to get the CPU up and running, and turn off all unnecessary and unwanted interrupts as fast as possible. And along with that, the VDC might be generating interrupts as well. So here's where we turn this off, using special instructions that are on the PC Engine. STO, ST1, and ST2 are actual instructions that are unique to the 6280. These basically bypass the accumulator and write the value, the immediate value that's in the operand, directly to the VDC, the video processor, and it writes to those registers. So this is the quickest way to hard code VDC writes without having to load accumulator and store to 0000 and 0002, etc. So these are shortcut instructions to write to the VDC. ST0 writes to the address or the register set register that's in the VDC. So that's 0000, and ST1 writes the lower byte of data. ST2 writes the high byte of data, because remember, it's a 16-bit video processor. Register number 5 controls the interrupts that come from both the V blank and H blank, as well as the lower bits here. Controls the interrupts for V blank and H blank, as well as turning background and sprites on or off. So if you set it all to 0, then interrupts are disabled coming from the VDC, and the background and sprites are both turned off, which means that the screen will be totally blank. So no garbage will show up on screen. So this will set a black or just the default screen. Okay. All right, so that's basically what we need here. Maybe just to test out that our RAM is mapped in and everything's working, I'll have an infinite loop here. Loop, I'll just call it loop, and branch back to the loop, so it shouldn't do anything bad. And let's load A with anything, beef, dead beef, whatever. Sorry, forgot to make that hexadecimal. Okay. Store that to 2010 in RAM. Alright, so that should be stored to RAM, and I think I'll push that as well, just to check that it actually works. And I'll decrement A, because this is a 6.5 CO2 instruction, and I'll push that as well, and that should show up on the stack as well in 21FE. That should be AD, and 21. That should be a decrement. That should be AC, and 21FF should be AD. And so we'll test that out right now. Okay, I guess I should put a comment here too. Let's see. Disable VDC interrupts. Screen off. Yeah. Let's see. The lower nibble of register 5, the low byte of register 5, turns off the various interrupts: sprite, overflow, interrupt, vsync, hsync, and I think the top two bits in the upper nibble of the first byte turn on and off the screen, the sprites and background. So there we go. Okay, so let's assemble that. Yeah, no problems. Then a listing file and a symbol file will get created, as well as the PCE ROM. Symbol just contains the labels and other variables that we've defined, and the list is an assembly listing with the opcodes and addresses right here. And it should match up fine. If we had, so up here list and mlist makes sure that the opcodes of our code and the listing get printed out, of course. If we didn't want them listed, for example, like if it's in a library that we don't want in this listing, or if we don't want macros expanded, I guess we type no list or nom list, no macro list. Alright, so that should match up. And the vectors, well, the one vector that we need is there right now. So close that. Alright, and so let's run it. Alright, of course it's blank, you'll see nothing, and that's correct. Let's reset it. Hit F11. Of course, Alt-D to get into the debugger, and then S to single step, and then F11 to reset. So yeah, we first of all start up, set enable, set interrupt disable, disable interrupts, and then set high speed. So right now the CPU will start up in kind of a random order, a random arrangement. So you know, all of these registers could be totally random, filled with FFs, we don't know. Of course, MPR7 will always be set to 0, so it'll always start up in this ROM. But all the other mappers are set to the same page, or the same bank in ROM, so even I/O and RAM are not mapped in yet. CPU speed is set to slow speed on startup of the CPU, so it's still 1.79 megahertz, as you can see here. And the VDC is probably set to something random too. Here's the control register. Let's say it's, for example, totally random. like that, and the processor flags are also totally random, like that. So you can see everything's turned on here. So SEI turns off interrupts. CSH will set the CPU speed to high mode. So now the speed is 7.16 megahertz. Clear the decimal flag in this processor flags register. So there, now decimal mode is turned off. So standard 6502 style reset. Then bank FF is the IO, and that'll be transferred into 01, or sorry, MPR 0. And so you can see here, even though we typed in TAM 0, it'll translate that to a bitwise 01. And then down here, TAM 1, that'll translate that into a bitwise 02. So there is a little difference between what we type in the assembler and what actual byte gets put in the opcode. But you don't need to worry about that so much. We just have to write TAM, the memory paging register, 0 up to 7. TAM 0 up to TAM 7. And then the assembler will translate that into the bitwise 01, 02, 04, 08, etc. So, well, let's load IO in there. Load A with FF. IO is now transferred in. So that means the VDC, VCE, I guess audio channels are in there too. We'll transfer the value in A to the X register because we need it later. And then here, F8 is the RAM, and that'll load into MPR1. So right now in our 0 page, you can see it's actually our ROM data. So everything here is ROM until we actually map it in. So there we go. You can see the ROM disappears, and now it's actual uninitialized RAM. We'll transfer X to the stack pointer because our RAM is now available. We can jump to subroutines if we want. Here we'll read the status register, the status flags of the VDC, just to disable any pending interrupt flags. Then we set the interrupt disable flags in this interrupt register right here, IRQM, IRQ mask. Got it set there. You can probably check the status of it in the assembler. Yeah, IRQ mask. IRQ2 is disabled, IRQ1 is disabled, timer is disabled, so they're all disabled right now. And then we'll set the control register in the VDC, this one here, which I set to garbage. Right now everything's turned on, so that is a possible state on startup. You never know. So first we store 05 into this register select, VDC register select register, and there it is now. And 05 is this CR, control register. And then we set the control register to all zeros to turn off the screen and turn off all types of interrupts from the VDC. There we go. And now background is turned off, sprite turned off, V blank, RCR, H blank IRQ are turned off, sprite overflow IRQs and sprite hit IRQs are turned off. Those are all the interrupts there. And so now I'll just set RAM to something that we can verify that it works. You write dead into 2010, 2011. There we go. And then we'll actually push that on the stack as well. So if you do Alt 3, you can check out the CPU, RAM, etc. So here is our dead in RAM. And actually here is our stack page. So push that. There's AD, and then decrement A, AC, and then push that to the stack. There it is. Okay, so stack is working fine. And then we'll just loop infinitely here. Okay, so that's a quick sanity check of our programming, the assembler and the emulator, and everything's working fine. So we can move on from here. Alright, and now it probably feels a little anticlimactic having working ROM but leaving the screen totally black. So I'll show the quickest way to get something actually displaying on the screen. Just to show that the program is actually running, and you can view that in an emulator or on real hardware. So at the bottom of our infinite loop here, let's just have it write to the palette over and over and over. We don't need to do any timing or wait for vblank or anything. The PCEngine is quite lenient that way. So let's see. Let's store 0 to 0402, which is the low byte of the palette index register in the VCE, the video color encoder, I think. And the high byte, we'll do it outside of the loop, of course, because that doesn't change. There we go. So XLE1. No, Mr. X. 0403. So 0402 and 0403 are a pair of bytes that'll send a 16-bit word to the color index register, and so that will come out to 100 hex. So that's 256, which is pointing directly to the color 0 in the sprite palette group. Let's see. I don't care what A is right now, but we'll just store it to 0404. Which is the low byte of the palette data register. And if we increment that, well, it'll just cycle over 256 different colors. But I don't know, why not just show the whole palette at the same time? So we'll increment another value, or another register. So that increments A, and then once it loops over, back to 0, it will increment Y, the Y register, and store Y to 0405. Okay, so that sends a 16-bit value to the palette data register, because the PCEngine's palette data, each color is defined by 9 bits, which will have to fit into 16-bit registers. Alright, and then that'll just branch back to the loop. Maybe I'll slow it down a tiny bit. There you go, and that should work. So I just push A, pull A, push A, and pull A, just to delay the CPU a tiny bit. It's a manual delay. Okay, so let's assemble this. And no errors, no problems. Run it in Mednafen again. Yeah, and here you can just see it's color cycling through all the colors on the PCEngine. If you run this on a real PCEngine, it should look exactly the same, because Mednafen's a pretty accurate emulator. And as a matter of fact, I took a screenshot from Mednafen, and this is what it looks like. And I actually loaded up on my PCEngine and took a snapshot of the TV screen, or the My Monitor screen, so this is what it looks like on the real PCEngine. It's, well, virtually identical. Alright, and that's pretty much the end of this tutorial. We've just got some things working on screen, and we've checked that the RAM works and our programming in assembler works fine. So we'll maybe get a bit more elaborate in another video. Thank you.